Okay, this is going to be part 1 of exam 3. And right here, as you can see, we're asked to write down the set of Crank-Nicolson finite difference equations, paying special attention towards explaining how I've arrived at the finite difference equation for the insulated boundary. So basically we have a 50-meter long bar with the left side suddenly increasing to 50 degrees Celsius and the right side remaining perfectly insulated. So it asks us to plot a temperature profile of the bar for every 5 minutes for 1 hour, and we are given what delta X is and delta T. And it also says for no heat transfer to occur at the insulated end, which is TJ plus 1. That TJ plus 1 is going to equal TJ, just because it's not going to change. It's never ready to change. Okay, so for part 1, to start with our Crank-Nicolson equations. Actually, I'm going to switch the background here. That way we can see what we're doing. Okay, so I'm just going to go ahead and scoot over. So what we can do is start with an energy balance from no volumetric energy generation, which we did in class, which ended out to be change in temperature over change in time equal to the thermal diffusivity with the second derivative of this guy. Now, to get an approximation of the derivative with respect to position, what we can do is we can have TJ plus 1 minus TJ to the n over delta X, and basically this is a finite difference. So this is dt over dx, the change in temperature over a change in position. So if we've got a long bar and this is one end and this is another end, what's the temperature at this point, the temperature at this point, at this point, and basically just as we go across, the temperature is going to change with time, and the temperature is also going to change with position. So this is that's one equation that we've got there, and another one that we can have is TJ n minus TJ minus 1 n over delta X. Now this is accounting for a forwards position, moving forwards in position, and this is accounting for moving back in position. And this is also a form of change in temperature over change in length. Now what we can do to get this term here for this energy balance is both of these are finite difference. These are both approximations of the derivative with respect to position. Both of these two finite differences are. So we can take these finite differences and take a finite difference of both of them. So we can do TJ plus 1 n and minus TJn over delta X, so the first finite difference, minus the second finite difference, and then all over delta X. So this here is the second derivative of that. That's the wrong spot. I did that here too. Okay, so that's our approximation of our second derivative there. And basically what we have now is we need to do for this guy, this part of the equation, We'll go ahead and move it over. It's kind of in a weird spot. We also need to take a finite difference of this with respect to time to give us an approximation of the change in temperature over the change in time. So I'm going to put that here as a term. So I'm going to do dt over, or d big T over d small t, change in temperature over change in time. And this is going to be at any position, n plus 1 being the time after, so a time in the future, minus the temperature at any specific time. So this is going to be the temperature plus delta T, so at a later time. And then we're going to do divided by delta T, so that's our finite difference, an approximation for that derivative. And now we can go ahead and plug all three of these into that equation. Right? I shouldn't say all three of these because we did an approximation for these two. So we can go ahead and plug these two in there for these terms. So for this equation, what we're going to end up with is Tj n plus 1 minus Tjn over delta T is going to be equal to alpha times, and these are just going to drop down. These are all in the denominator. So it's going to be Tj plus 1 n minus Tjn, and this negative sign is going to get distributed. And this is all going to be over delta x squared. And now we can just continue with our algebra. Just rearranging things, adding things, combining like terms. And then you're going to end up with Tj plus 1 to the n minus 2 Tj n plus Tj minus 1 n. And actually, we can go ahead and pull out that delta x, or that delta x squared rather, and just leave this in there. I'm going to go ahead and move this down. It's kind of close together. Alright, so if we were to leave this equation the way it is and solve for the temperature, so like I could solve for this guy the way it is, and find the temperature at a later time based on all of these, which are Tjn. So the temperature at a specific position at any time. I could find the temperature at a later time based on the previous times. However, that creates a problem, and the equation would go all haywire. And it creates failure points. So in order to, because we're trying to simulate how the temperature changes with time, we can use Crank-Nicolson, which basically, instead of using the temperatures that we already know, we can take the average of the finite differences of the temperatures that we're trying to solve for. So what we can do is, I'm going to go ahead and move over this guy as well. That way it's out of the way. I'm going to go ahead and rewrite the left side of the equation and put delta T up here. So we're going to take the average of these guys. That's the Crank-Nicolson method. So what we can do is, I was going to put a bracket around this so it makes it a little bit easier to look at. And I can go ahead and do Tj plus 1 n minus 2Tj n plus Tj minus 1 n. And since I'm going to take the average of these, what I can do is take the average at the current time and one at a later time. So basically I'm going to take average of the same exact thing, so Tj plus 1, except for this is going to be n plus 1, so at a later time. And this is all going to be over 2 since we're taking an average. Okay. Now I'm going to go ahead and pull out this 2 and redefine it. I'm going to define this since it's I just don't want to keep rewriting it. So I'm just going to call it r, and that's just going to be equal to alpha delta t over 2 delta x squared. And rewriting that here, Tjn plus 1 minus Tjn is equal to r Tj plus 1 n minus 2 Tj. Actually, we can go ahead and take these parentheses out. And then we're going to be left with Tj plus 1 n minus 2 Tj n plus Tj minus 1 n plus Tj plus 1 n plus 1 minus 2 Tj n plus 1 plus Tj minus 1 n plus 1. Close both of those. And then we can go ahead and distribute the r into here, to each term, and then just rearrange it. I'm going to put all of the n plus 1 terms on the left side, because that's what we're going to be solving for, is the temperature at a later time. And I'm going to put all of the n terms, so all of the temperatures at the current time at the position, on the right side. So rearranging that, that's going to give you minus r Tj minus 1 n plus 1. That looks really bad. I'm going to redo that. So minus r Tj minus 1 n plus 1 plus 1 plus 2r Tj n plus 1 minus r Tj plus 1 n plus 1. And that's our left side of the equation. And that's going to be equal to r Tj plus 1. And it's basically just going to be the same exact thing, but since this is on the other side, this is going to be a minus. And this is Tj to the n. Alright, so for every single node, this equation is going to be true. However, the difference here, if you go back to the problem statement, it says no heat transfer to occur at the insulated end, and that Tj plus 1 is going to be equal to Tj at that point. So it says to solve T49 and involve the equation to solve for T49 will involve T50. But the difference is the fact that this is going to be your T50, this would be your T49 in a sense. So what we can do is go ahead and apply that. So I'm just going to write a side note in here. We'll go ahead and, is blue dark enough? Yeah, we can see blue. Okay, so all nodes except 49. And this is just going to be this whole equation. I'm just going to put a little weird circle around it. So if we plug in the fact that Tj plus 1 is equal to Tj for the 49th node, just to note that no heat transfer occurs at node 49. So I'm just going to go ahead and substitute that real quick into this equation here. I'm just going to bring this down. Okay, so I subbed this guy. That was a J plus 1. So the next position. So the temperature at the next position is going to be the same as the previous for node 49, just because it doesn't change. So this is going to be Tj now, same because this is J plus 1. Okay, so this is for node 49, and notice these guys are like terms, and we can go ahead and add this into here, into these parentheses, and same thing applies on the other side of the equation with this guy. So now our equation for node 49 is going to be negative R Tj minus 1 n plus 1 plus 1 plus R Tj n plus 1. This guy is he got put in there. That's our left side of the equation. Now our right side of the equation is going to be the same thing, but this is going to be minus. So Tjn plus R Tj minus 1 n. So node 49. So those are our two Crank-Nicholson equations that we need to recognize. Now, if node 49 was not perfectly insulated, it would have the same equation. It would also use this equation, but because it's perfectly insulated, the previous temperature is always going to be equal to, or I should say the new temperature is always going to be equal to the previous temperature. It doesn't change. So you can go ahead and apply the fact that Tj plus 1 is equal to Tj and come up with this new equation here. And in your matrix for this, you'd have your coefficients in here. So 1's always going to be on the outside for Python. So I'm just going to put this as outside. So you have 1 plus R here. And so basically you have Tj minus 1, and then you have Tj here. And then here at this next one, you'd have Tj plus 1, but we don't have that. So ours would be 0, and it's always going to shift. So we're going to have minus R here, and then 1 plus R here, and then 0, and then these are all going to be zeros, however many we got. And this is for the top side of the vector. And for the back side, we're going to have the same exact thing, except it's going to be backwards, so it's 1 minus R now for this other side of the equation. But here we're going to have our 0 out here, because this is Tj plus 1. Like I said, that doesn't change on the right side. That's always going to be the same. And this is minus R, and then the same thing's going to happen. It's going to shift at this level here, and it's basically just going to create diagonals. So you're going to have a diagonal here and a diagonal on this side. So this is your middle diagonal, and you have one diagonal below that. But you don't have a term here to make a top diagonal, so you've only got 2. And that's the end of part 1.